Hello, everyone. Welcome to our live session. This is kind of a makeup live session. I mean, we still have 2 a month, but this is kind of a live makeup session for last week. We are excited to be here. It's been a few weeks. And so again, my name is Matthew, and I am one of the course instructors for our online classes, but we know that many of you come to us from a variety of places, and we are happy to have you here. I'm going to let Professor Impey introduce himself, and then we will get to your questions. Please post those in the chat. We grab all the questions from the chat, and we see everything. So don't post over and over and over again. We don't need to spam the chat. We will get it, but we also jump around to a variety of topics. We try to keep it at an introductory level. So your most advanced hypothetical physics questions may not be addressed. We're not ignoring you. We just need to keep this at a level for everyone. So Chris, go ahead and say hello to everyone, and we'll get started with questions.
Okay, welcome everyone after a little break. Always a lot going on in astronomy, so I'm glad to have you here, however you found us, through taking one of the MOOCs or just otherwise. So we're ready to go and open for any question on astronomy.
Excellent. The first question is from Rama Ranganathan, who says, "Good morning, Professor. One of the theories on the origin of organic life forms on Earth is that some meteor or stellar object, or sorry, I guess it's a stellar object, I assume they mean interstellar object, delivered a life form containing chemicals on Earth. What are your opinions on this?" I guess I'm missing the second half of the question. What are, considering the amount of time such chemicals could remain stable, is there a time limit to how far in space we need to search for extraterrestrial life similar to Earth?
So these are kind of distinct questions. So I'll answer the first one about the delivery of chemicals to the Earth on space rocks, essentially, whether it could be meteors or comets. So this is a long-standing idea. It's called panspermia, actually, has a name. And so the idea has been around for over a century. The idea that life propagates, inside space rocks, and that seeds on different planets and different bodies around not just our solar system, but other solar systems by this kind of delivery mechanism. At the moment, it's not the best guess for how life starts or spreads. And that's because the level of complexity of chemicals that have been found in meteors, meteorites, or comets is fairly simple. So there are molecules, there are a few amino acids, there are small, short carbohydrates, but these tend to be molecules with no more than 20, maybe 25 atoms. So they're not long molecules. They're not extreme carbon chains. They're not anything like RNA or DNA, a replicating molecule. So these are really just the very primitive building blocks of life, and they exist on the Earth, and of course they can be delivered from space. So there's no obvious sense that delivery by rocks accelerates the process that would always be underway anyway with those ingredients there on the Earth's surface. The idea that a space rock can contain a full living life form and transmit that is another idea that we haven't really yet tested. There are simple experiments that have shown that microbes could go into a sort of wait state or a dormant state and survive inside a rock dry for a long period of time. And then the same microbes could survive in space for a long time, because inside a rock, it's a protected environment. It's shielded from cosmic rays and the vacuum of space. And the estimate of how long life can persist is up to 10, maybe 20 million years. And that in principle is long enough for a space rock to travel between star systems and land on another world with a microbe that might get reanimated by water, say. But this is very unlikely stuff, and people have done the probability of a space rock traveling between star systems, and it turns out to be very low. So it's not really a plausible mechanism for life either starting or propagating.
Excellent, thank you. The next question is from Yangip, who asks, "Is space, and especially time, absolute? Is the Big Bang a physical..." Oh, I guess we'll start. That's the first question. So is space, especially time, absolute?
There are concepts of absolute space and time, but most of the concepts of space and time are not absolute because they're framed in terms of relativity, special or general relativity, Einstein's theories. And in those And in those theories, time is of course supple because time dilates according to the speed. And in gravity theory, time dilates according to the intensity of gravity. So time is very definitely not absolute. It depends on the local circumstance of gravity and the local environment and relative velocity. Space is also not absolute because while we can imagine a grid of three-dimensional space and mark it out, general relativity says that space is curved according to the mass and energy that it contains. So space curvature in 3 dimensions, which is a little hard to visualize, definitely happens because we have evidence of gravitational lensing from many sources and many beautiful pictures from the Hubble Space Telescope. So space is not absolute and nor is time, and their flexible relationship with each other and with a possible absolute framework is defined by relativity.
All right, the next question for those of you who are on with us live, yes, just submit questions through the chat. We will grab them from there. I'm monitoring it, and Vicky is here monitoring that. The next question is from Lawrence 4041. Does the many worlds theory basically explain away the weirdness of quantum entanglement?
So the many worlds theory was put out by a physicist called Hugh Everett in 1950, I think, and was developed through the 1950s. And it's an alternative to the standard or Copenhagen interpretation of quantum mechanics. The standard model of quantum mechanics, really fronted by Niels Bohr from its inception, is that we have to accept a probabilistic view of nature, that particles don't have absolute positions, they have probability distributions, that energies are quantized and also don't have an absolute distribution, but a probability distribution. Pretty much any quantity we can measure. The many worlds idea just replaces the probability distribution with a series of branching points, where when we actually know what a particle is, and we say it's in this position and not that position, that corresponds to a branching of universes, where the outcome we observe is the universe and the path we follow, and the alternative path branches off. And so in the many worlds theory, it's pretty extraordinary because each of these probabilities becomes a branching point in a universe propagating forward in time. And there's essentially infinite branching points. So this is a pretty radical idea to replace probabilities distribution with branching points in parallel universes. Indeed, if you accept the Everett theory, then entanglement is not a relevant concept because the particles will cohabit in one branching point of the space-time, but there'll be another branching point where they don't commingle, and so you don't have entanglement. But no one's really figured out a way to test the many worlds hypothesis in the half century or more since it's been around.
So that kind of addresses the second part of the question, which was, is it a viable explanation for reality? Excellent. All right, the next question is from an email from Mahesh Devarakonda, who says, I would like to know if there is something like a cosmic horizon where older galaxies set, i.e. go out of view, and newer galaxies rise, similar to the horizon as we see from Earth, where the sun rises and sets along with the stars.
So it's a good question, and it acknowledges that there are different horizons in physics and astronomy. So there's the terrestrial horizon that's familiar to us on a curved surface. There's a region, if you're out on an ocean, where objects have disappeared below the horizon, and that represents the edge of our view. In black hole physics, there's an event horizon, which is an information boundary or membrane where nothing can be seen by us inside the event horizon. And in cosmology does have its own version of a horizon called a cosmological horizon. And these are regions of space which we believe to exist based on the Big Bang model, but which we have not seen any information because light has not been able to reach us in the 13.8 billion years the universe has been around. So that's beyond our horizon. As for the question of galaxies coming and going relative to the horizon, that's a very interesting idea, and it does actually exist. So the early universe was expanding so fast that galaxies were moving away from each other at the time their light was emitted faster than light speed. So that means you couldn't see that other galaxy. but the universe decelerated in the first billions of years of its existence, and that allowed light from a more distant galaxy to reach us. So in the early universe, there were definitely galaxies that we could not have seen that eventually became visible as the universe evolved. Now, more recently, the universe is accelerating in its expansion, and that's going in the opposite direction. That means galaxies that we can now see that are within our horizon will actually eventually become beyond our horizon, because they will start moving away from us faster than light speed. So you can go in both directions in the history of the universe. You can have galaxies that are within our horizon that move out of it, and galaxies that are out of it that move back into it. It's an interesting concept.
Excellent, thank you. We have kind of a pair of questions that are related to each other. So Enceladus Luna asks, how did gas planets form?
It's not fully known. There are theories, but we haven't tested them enough to be totally sure. But the speculation is that all the planets, whether they're gas giants or terrestrial planets, have a rocky core. And we know from indirect measurement that Jupiter and Saturn have rocky cores, and we very strongly suspect that Uranus and Neptune have rocky cores. So the seeds for all planets in our solar system, and we think the other planets, are small rocky objects. Now, the outer planets, because there's more material at the large distances, those rocky cores could be 3, 5, maybe 10 times Earth mass. So these are large rocky cores. And then what happens is, because of the large amount of cool gas and that far away from the sun in these large orbits, this gradually gets accreted onto the rocky core. And so it ends up with a very thick mantle of gas. And of course, eventually the gas far outweighs the rocky core at its center. And so that's how you grow a gas giant. And in the models and simulations, the growth of an object like Jupiter or Saturn from the starting point of the accretion of its rocky core need only take about 10 or 15 million years. So that's actually a very rapid process. So we don't really know how to test this model very accurately or precisely or securely, but that's the best that observation and simulation suggest so far.
All right, the next question that's sort of related is from an email. Wendy Traver asks, can you comment on the newly discovered exoplanet, which is AB Auriga B, and why there are more gas giants than rocky planets in general?
So there are, as the number of exoplanets climbs, and it passed through 5,000 exoplanets on the NASA website in February, I think, or early March. As we find more, obviously we are finding a lot of gas giant planets. Remember, the gas giants are on large, long orbits, so finding them by the Doppler method needs multi-decades of data. And so we're starting to find gas giants in normal architectures like our solar system for the first time. But there are gas giants, and there are some that are as much as 8 or 10 or maybe even 15 times the mass of Jupiter, and that's about the maximum. That's the limit pretty much for a planet. And the AB Auriga system is just a very young gas giant in the process of forming. So it's a very important system for testing the formation of gas giants. But there is a natural limit to the formation of a gas giant, and it just relates to the amount of material that's available in a protostellar disk that is therefore available to build planets. So the planet building reservoir is not infinitely deep, and planets can only form in sort of sectors moving out from the center of where the star is. So there's a natural limit to the mass of the gas giants, and we found some that we think are very near that natural limit.
The next question is from H. Bin Biham, who asks, please talk about baryon acoustic oscillations, their origin and use by Roman and Desi to map cosmic expansion.
So baryon acoustic oscillations is a phenomena, and it's abbreviated as BAO, and it's a pretty standard acronym in cosmology. These relate to the behavior of the plasma in the early universe. So when the universe was very young, there were interactions between the radiation and the high energy particles of the early universe. And of course, these particles were before 400,000 years after the Big Bang, when stable atoms formed, these particles were free from the nuclei. So the protons and the electrons were traveling freely. And you can think of a plasma as a fluid in the early universe. And just like any fluid, you can get oscillations set up in a fluid. There can be standing waves, there can be pressure waves, and the baryon acoustic oscillations essentially are the modes of oscillation of this plasma of the early universe as the universe expands. And so we are trying to look for the imprint of the characteristic wavelengths of these oscillations in the eventual galaxy distribution that formed. So these standing waves and oscillations are set up quite early in the history of the universe, and they have particular scales that are based on the temperature of the universe at the time the oscillations form, and the size of the universe at that time. And these map forward into potential imprints on how the galaxy distribution is now, currently, in the nearby universe. And so the test of baryon acoustic oscillations is to look for patterns in the distribution of galaxies on very large scale that reflect the imprint of density changes and oscillations in the plasma that preceded them. And that has been found. And so about 10 years ago, the first baryon acoustic oscillations are found in ground-based galaxy surveys. And since then, we found other imprints. So it's a very new and not an interesting way to test the physics of the early universe.
The next question is from Damata Fakar, who's on with us live. How does the moon affect the tides on Earth?
Well, the moon causes the tides on Earth. In the solar system, the moon is anomalously and unusually large compared to the planet it orbits. There's no planet elsewhere in the solar system that has as proportionally large a moon as the Earth does. Venus is the Earth's twin and has no moon. Mars is a smaller object than the Earth and has two very small moons, Phobos and Deimos. So, and Mercury has no moon. So the moon is, our moon is really unusual. And it's close enough to the Earth that it's tidally locked. So the tidal interaction is what keeps one face of the moon facing us. So the fact that the moon is large and the fact that it's tidally interacting with the Earth is what leads to the tides. And the gist of it is that the force of the moon on the near side of the Earth, just using Newton's gravity law, is more than the force on the moon on the back side of the Earth. And that amounts to a stretching force. That stretching force, of course, applies to the Earth as a planetary body, but it applies more readily to the liquid, the ocean, that is able to flow in response to that stretching force. And so in response to that stretching force, the oceans bulge forward towards the moon and away from the moon in the opposite direction. And that, of course, means when the Earth rotates, you have 2 tides a day in a 24-hour period. That's the basics of the tides and why they happen twice a day. The details of the timing of tides obviously relates to the topography of the Earth and the shape of the coastline and so on. So you need tide tables, and local, deviations from the overall 24-hour pattern are quite strong depending on local topography. But that's the basis of it.
The next question is from an email. I just read that a scientist has proposed that information may have mass and could be the 5th form of matter. What do you think about this idea?
Well, I'm not sure of the work that that's referring to. The concept of information having mass is interesting. It's not, I can think you can imagine an implementation of information where it has mass. I guess the most foundational way to think of this is, what form of information are you talking about? If you have information that is somehow related to energy storage, we think of binary digits, 1s and 0s, but that also could be bright and dark, or on or off. It could be a higher and a lower energy state. So if your information storage somehow maps into energy, then through E = mc squared, yes, information that is coded somehow in terms of energy does have an equivalent mass, a very small amount. That's probably the only way we could really think of information as having mass.
SST11 asks, before the Big Bang, what was there in space?
Before the Big Bang, we simply don't know. The theory of cosmology, the Big Bang theory, is a description physically of what happens from an early, hot, dense state. And most of the research is involved in how far back can we push the model towards the inception. Now, if you just project back the initial state, you predict infinite density and temperature, which is non-physical. So essentially, the Big Bang model does not work at the origin because we don't have a quantum theory of gravity. And it's the same when it comes to what caused the Big Bang or what came before. Because we don't have a physical description of that initial, the truly initial state, we can't therefore speculate as to what caused the Big Bang or what came before it. So while it's tempting to speculate, we're not in sufficient possession of a physical theory that allows us to do that meaningfully.
The next question is from Astrocellist, who's on with us live. Hello from the UK. I have a question on black holes. I understand that nothing at the speed of light or slower can escape, and gravity travels at the speed of light. So how does the gravity escape the black hole to affect its surroundings?
So the gravity escaping at the speed of light or traveling at the speed of light, that's a concept, that's an extension of standard model particle physics, which has that the four forces of nature, the fundamental forces, have particles that carry that force. And so in the standard model of particle physics, where you have a photon carrying the electromagnetic force, you have the W and Z bosons carrying the weak force and quarks carrying the strong force, there's a graviton that carries the gravitational force and propagates at the speed of light. But that's sort of classical standard model physics, and it fails to account for the situation of a black hole, because the black hole, of course, is defined by general relativity. And general relativity will say that the light is trapped because of the curvature of space-time. So it's a quite different explanation. So it's not ballistic and it doesn't involve particles traveling at a particular speed. So I would say that we have to think of black holes using general relativity while recognizing that the theory is incomplete.
The next question is from an email. David McKenzie asks, is it possible that life could originate and flourish among globular star clusters such as the Pleiades? From what I understand, they are very old stars that lack elements that we see in our solar system.
So I'll answer a question about the globular clusters. The Pleiades is actually a young star cluster, so it's not a globular cluster. But as far as globular clusters go, yes, these are old stars. They're primordial. We think they formed in the halo of mostly of our galaxy early on, maybe 10, 11, 12 billion years ago. And their stars are, of course, very old. And because their stars are very old, their stars formed with relatively small amounts of heavy elements, because there had not been time in the universe to form a lot of nitrogen, carbon, and oxygen and ejected into space to become part of other stars and planetary systems. So it has long been thought that a globular cluster would be an unlikely place to find a lot of biology on planets around those old stars, because those stars are so poor in metals or heavy elements, including carbon, the essential life element, that maybe there's just not enough carbon or heavy elements, even maybe to form planets in the first place, let alone biology on those planets. That is just a supposition, though. I think the truth is that it's not dramatic. We found old stars that do have planets, exoplanets, so we know that there's enough material to make exoplanets, even in old stars with generally low metal abundance, as astronomers would say. So I think it's not quite clear cut. But yes, the probability of biology in a globular cluster is lower than the probability of biology in the Pleiades, say, or in the region around the sun.
JMDM Astro asks, oh, I'm sorry. Next question is from Unstarman, who asks, can one deduce the shape of an exoplanet's orbit from the shape of the curve of its wobble, such as those in our week 2 problem?
Yes, I mean, you get information on the orbit of an exoplanet by following the wobble. I mean, it's a timing experiment. So the best information we have on exoplanet orbits involves very careful timing experiments. And actually the best information comes not from the Doppler method, it comes from the transit method for exoplanet detection. And those methods, those timing observations of exoplanet eclipses have indeed been used to define the eccentricity or the nature of the orbit.
The next question is from JMDM Astro. The universe expands in all directions about 46 billion light years. So we would be in the middle. I don't understand how that works. And then I'll do a follow-up after that.
So it's tricky, because we look out in every direction. As we look out, we look back in time. That's finite speed of light and the great distances in the universe. So while it is true that the edge of the visible universe, the edge of our cosmological horizon, is 46 billion light years in every direction, that by no means implies we're at the center of this universe. Because if our position were transposed, if we lived on another galaxy, we would witness exactly the same thing. We'd look out to 46 billion light years in every direction. So it's a democracy of perspectives in this. There's no Copernican principle violation here. Every galaxy will see the same thing. As for the reason why there is a limit, that is essentially the distance out to which galaxies' light has had time to reach us in the age of the universe as we measure it, 13.8 billion years. The reason the horizon is 46 billion and the age of the universe is like 14 billion, that's a factor of 3 difference between those numbers, is because the universe was expanding faster than light for a first part of its existence.
And then the next sort of part of the question is they would like you to explain how the universe is flat. Like, what does it mean that the universe is flat?
So it's an empirical observation that the universe is flat. The universe originally in its early state was extremely knotted space-time. It's very high density, very high temperature, and very small. So gravity was intense, and I'm sure space-time was highly convoluted and certainly curved. The fact that the universe has expanded an enormous number of factors of scale since the Big Bang is what really makes space flat. So as the universe has expanded, it's sort of flattened space out. And the most dramatic flattening of space occurred in what astronomers call the inflationary era, in the first fraction of a second. That's what really took the highly curved space-time and made it essentially flat. Now that's the theory. The evidence that it's the case comes from observations of the microwave background radiation. So that radiation is seen across space and time to almost the dawn of time, 400,000 years after the Big Bang. So it's seen across almost 14 billion years of light travel time. And we can see how space either amplifies, de-amplifies, or doesn't amplify at all the size of the speckles in the microwave background radiation. And compare it to a model, and we can easily see that they are neither amplified nor de-amplified. In other words, the space along the way between the dawn of time and the microwave radiation and us now, 14 billion years later, it seems to be spatially flat to quite a high degree of precision, within 1% or so.
The next question is from an email from Hernan Reyes. Since the discovery of huge numbers of exoplanets, much research has been done on what role a planet's obliquity can play in determining its eventual habitability, and hence the possibility of life developing on it. Let's see. Could you please give your explanation for the apparent crucial role of planet obliquity?
So obliquity, first of all, to define it, is the tilt between the spin axis of a planet and the plane of its orbit around its star. So in the case of the Earth, that tilt is 23.5 degrees. And that's, of course, what gives us our seasons. So the first reference point on exoplanet obliquity, the tilt of their spin, and habitability, is that it gives the seasonal variations. And we're very familiar with the seasonal variation on an Earth-like planet, the Earth, that results from a 23.5 degree tilt. The question becomes, what tilt is necessary, or is any tilt necessary, or what tilt is too much for habitability on an Earth-like planet? So it's a very interesting question. Astrobiologists have wrestled with it and struggled with it because we don't always have enough information to decide. But the best guess is that the habitability of the Earth was helped not so much by the obliquity being the number it is, 23.5 degrees, but by the fact that that obliquity is stabilized by the moon. So the large moon that we have has stopped that obliquity from varying wildly over the history of the Earth. The best guess is it's only varied by a couple of degrees. Contrast that to Mars, which currently has similar obliquity to the Earth, but where that number has varied from probably 20 degrees to 45 degrees over time, because Mars is not stabilized by any moon and subject to perturbation by other planets. So in a planetary system, other planets, absent stabilization by a large moon, are going to perturb the obliquity and possibly change it by large amounts, and that may reduce the habitability of a planet. It's still an open question as to what is too much obliquity. if you have a Uranus type situation where a planet is essentially tilted on its side, 87 degrees or 90 degrees, that generates extremely strong seasonal variations, but is it enough to suppress life? And the reason there's no simple answer to this question is because the models have to account for the presence of oceans and land masses and do atmospheric modeling. For example, the climate on the Earth, caused by our tilt, the seasons, are only explicable once you take into account ocean models of temperature and transmission into the atmosphere and climatic patterns and so on. There have been recent papers that suggest that you could still have habitability even with large obliquities of 50, 60, 70 degrees for an Earth-like exoplanet. So it's not clear that the large obliquity rules out habitability. That is still active research, but it doesn't seem like it necessarily is the case. It leads to some more extreme climate variations, but life has been sturdy and adaptable enough on the Earth to handle 2 snowball Earth episodes, we think. So it's clear that it's not clear that that's a single determining factor for habitability.
That's excellent. And that answers the second part of his question, I think. How did Earth survive multiple episodes of snowball Earth?
Well,
and
that's a different enough. Okay, I'll answer that as a different question. Okay. So the question of how Earth survived 2 snowball episodes is a good question, but it begs the question, you know, how do we know that the Earth had 2 snowball episodes? And I would say it's not absolutely beyond any reasonable doubt that the Earth did have 2 snowball episodes. So what are we talking about? We're talking about a time 2.2 billion years ago, roughly, and then a time more recently, about 650 to 700 million years ago, before the Cambrian explosion, when the Earth climate became unstable and the feedback set in such that it cooled dramatically and froze to the point where there might, if not the whole planet frozen just like a block of ice, there might only have been a thin girdle of oceans at the equatorial regions for some period of time. So it goes into that cycle, into the snowball phase, due to sort of a positive feedback loop that happens in the climate, you know, where eventually when there's more ice forming, of course, once you start forming ice, perhaps just because volcanism slows down, you can have a low geological activity, so there's less carbon dioxide, there's less greenhouse effect. Once you get to be able to form ice, you reflect more of the sun's light, which decreases the temperature and lets more ice form, and then you head straight into a snowball phase. And there was some indication that it's certainly in the early snowball episode, where the evidence is not quite so good because it was a long time ago, that the Earth came very close to never getting out of it. It might have been in the snowball phase forever, which would have dramatically affected how life evolved on the Earth. But eventually what happens is geological activity kicks in, volcanoes start poking up through the ice and punching holes in the ice and putting carbon dioxide in the atmosphere. The greenhouse effect warms the atmosphere, which melts the ice, etc. And so you can reverse that positive feedback loop. So it's very interesting nonlinear atmospheric dynamics that lead to these snowball episodes.
David Learning asks, with the sun projected to turn into a red giant in roughly 5 billion years, is it inevitable that planet Earth will no longer be habitable for humans at that time?
Yes, I think it's pretty inevitable. And actually, it's going to happen well before the red giant phase. As the sun evolves, and the sun halfway through its main sequence life, converting hydrogen to helium, it reconfigures, it resettles, because it's changing, obviously, its chemical composition. It's converting hydrogen to helium, and that causes a different equilibrium state of the sun. And what that actually does is it increases the core temperature and therefore the mean photospheric temperature and the radiation rate of the sun. So the Earth is going to warm up, and the best guess is that in just 500 million years, so well before the sun ends its main sequence life, the equilibrium temperature on the Earth could approach the boiling point of water. So the best guess based on stellar evolution is that the biosphere is only going to be viable for another 500 million years, not all the way to the red giant phase. And the red giant phase, of course, will fully extinguish it, because a hot envelope, the sun will bifurcate into a compact superhot core and an extended giant envelope that will pass the orbit of the Earth, and that will be the end of life on Earth.
Potato Lord 455 asks, is there a possibility of something to go in a negative entropy state, shown most notably in the movie Tenet?
It's possible in concept, and I think in physics too, to have a negative entropy state. Entropy is microscopically defined as the number of equivalent microscopic states. So high entropy means a large number of equivalent microscopic states, and low entropy means a low number of equivalent microscopic states. So negative entropy in that sense only makes sense in the interaction of a system where you have some change in a system that somehow lowers the number of equivalent microscopic states. That would correspond to a loss of entropy or negative entropy. So it's not possible to have a isolated system that has negative entropy, but in interactions between systems, the concept of negative entropy makes sense.
Enceladus Luna asks, how does Jupiter's gravitational force, or how do Jupiter's gravitational forces affect surrounding objects?
Well, Jupiter, as the most massive planet, has, of course, strong gravity. It has magnetic fields. It has a radiation, the extended radiation field around it. And of course, it has a large moon system. I think you could go down to the smallest moons. Jupiter moon count is now well over 70, 80, maybe even 100 if you go to the smallest objects. So Jupiter's gravity dominates all these things. And although it's not obvious and we don't think of it this way, Jupiter also has a very faint ring system that was seen by the orbiters that were sent out there in the 70s and 80s. So Jupiter's gravity dictates all of these things. It dictates the orbits of the moons and their interactions. It dictates the interaction of the radiation field with particles around it and the environment of the rings, the faint ring system. And most of this is pretty well understood because we know the mass of Jupiter fairly accurately.
The next question is from Hopadero. In Kenya, there is a place where water flows uphill along the road, and the same happens with cars who are in free gear moving uphill. In simple terms, how do we explain this kind of anomaly?
I think what I've read about these situations, and then I've heard about the one in Kenya, and I think there are other places in the world where this is seen, is this is pretty much an illusion of topography because, gravitationally, there's two possible explanations. One is that it's an illusion where the local topography can essentially fool you into thinking a little local region or a stretch of road or a particular piece of land is sloping a particular way when it isn't. In other words, fool you into thinking that it's a downhill. It's a trick of perspective, essentially. That's one possibility. The other possibility is that there's interior changes in density that affect the local gravitational field that might give this effect. So if you had, for example, a situation with very large metallic deposits just under the ground on a slightly uphill stretch, then the local gravity there will be quite strong. And in an adjacent region, you don't have those strong, highly concentrated metal deposits, the local gravity will be less. So local gravity could possibly vary by enough to make this illusion actually physically real.
Loki, who sent an email, asks, what are your views about habitating Mars? And if it's possible, in how many years do you see it happening?
I think the plans are underway in the private sector. Elon Musk, famously, who said he wants to die on Mars, has plans for a Mars habitat, his huge rocket that's undergoing tests right now and will start sending passengers initially, I think, into Earth orbit and then to the moon, but that's a stepping stone to Mars. He imagines this rocket will be starting to take passengers to Mars in about 10 or 15 years. So that's a rough time frame that SpaceX, as CEO, would give for habitation on Mars. For NASA, it's a much more tentative timeline. They're really fixated on getting some sample return going, and that itself is going to take 10 or 15 years. So I would say the governmental Mars base from the US government, NASA, or ESA, the European Space Agency, these are several decades away, 30 or 40 years. The wild card in all this is China, because China has big ambitions in space, and they're talking about a moon base and a Mars base, and they're investing enough in their space program with a budget doubling time of about 5 years that they could also get there in 10 or 15 years if they wanted to.
Next question is from Juan Kramal, who asks, as far as I know, the problem of infinity at the beginning of the universe and in the interior of black holes was in principle solved with the 4 superstring theories, and more particularly with D theory. What do you think about these infinities and the potential solutions?
It's certainly true that string theories, one of string theory's prime motivations was to circumvent the problem of cusps, density cusps, where in other physical theories. So yes, you have situations where in sort of classical standard physics, standard model physics, you have infinite mass density or infinite charge density in a particle, or at the inception of the universe, or in the center of a black hole, a singularity. And string theory, by positing tiny one-dimensional entities, space-time entities at the heart of all matter and at the basis of all particles, does indeed, almost by construction of the theory, remove the possibility of infinities. So it does take them away and out of the picture. That's the good news. The bad news is string theory at the moment is not tested, not well tested, and parts of it may be untestable in the near future because it operates on a spatial scale and an energy scale that is simply not accessible to experiment right now. So the only things people have come up with are very, very indirect tests of certain aspects of string theory. So I think that's the fundamental limitation right now. It's just the testability of the theory.
Slight Quills is on live and asks, are there any new strategies being developed to detect rocky exoplanets without the requirement of increasingly more powerful optics? And why or why not?
Well, the techniques for detecting rocky exoplanets, Earth-like planets, are pretty mature, and we know what they are. I'd say the one that has been that is new enough and hasn't been used on an industrial scale, in the sense that very few planets have been found that way so far, is microlensing. So we're very familiar with the Doppler method that was used for the first few hundred exoplanets, and the transit methods that's been used to grow the number from a few hundred to a few thousand, and both techniques have given us over 5,000 exoplanets. Microlensing is a very powerful method that has only, I think, discovered less than 100 exoplanets. But if it were deployed as surveys to do it on a much larger scale, it has a high degree of sensitivity, doesn't actually need large telescopes too, so it's not hungry for photons, because you're essentially looking for very rare events. And the amplification of microlensing is fairly easy to detect with a modest telescope. So the trick is just covering large areas of sky and looking for rare one-time events where a planet passes in front of a other star with planets, and you see a microlensing signature of the intervening star and then its planet. So that's the technique I think that could be used on a much larger scale in the future. And there are surveys that hope to take us from, dozens of exoplanets found by microlensing to hundreds of exoplanets. And it, in principle, has a sensitivity to go all the way down below Earth mass to Mars mass or even Mercury mass planets.
Steve Callender sent an email asking, hi, Professor, would you explain how a hot Jupiter like 51 Peg stops its inward migration and establishes an extremely close orbit instead of crashing into its star?
Sure. I mean, in the dynamics of planetary formation and evolution, it is indeed possible that the large planet in its migration does fall into the star. And some of the models that track these things suggest that most of the hot Jupiters in their migration phase actually fall into their star. So the star just consumes them and it just adds to the mass of the star. So depending on the orbital trajectory and depending on the interior density of the disk, because there's a gas disk, so there's a viscous force that's kind of slowing down the migrating planet, then it can get to a point where it tidally locks. And of course, at that point, it is in a sort of stable, tidally locked situation and won't fall further in. But in the totality of these situations, it is indeed likely that most of the hot Jupiters do fall into their stars, and only a small fraction become tidally locked and 51 peg-like planets that we observe.
The next question is from H-Bin Behem, who asks, the recently identified HD1 may have population 3 stars. Does this population designation indicate third generation stars, and will JWST give us a better look?
So the object alluded to, HD1, is a recent discovery of extremely distant, perhaps the most distant galaxy yet found, well within 500 million years of the Big Bang, so the oldest galaxy and the most distant galaxy. It is speculated, there's not a lot of data on it yet, to have population 1 stars, population 3 stars. Population 3 stars are the very first generation of stars that form really with very low amounts of heavy elements, because no heavy elements have been created. James Webb is indeed going to be deployed to looking at this object in the infrared, and there are certainly transitions in spectroscopy that can be done there that will pin the metallicity or the heavy element abundance of this galaxy. So it's a pretty exciting prospect.
Jan Campos asks, are open clusters found only in the disk of galaxies and globular clusters only in the halo? Aside from being clusters, they don't seem to have much in common. Is that true?
Yes, there's a pretty clear segregation between open clusters. Open clusters are loose aggregations of stars, not always large numbers, maybe thousands, tens of thousands, hundreds of thousands at the most. And they tend to form in the disk of a galaxy, and they essentially are outlining or delineating the spiral arms of the galaxy in a galaxy like the Milky Way. So they're young star aggregations, and we believe their star formation is triggered by density waves in the disk of the galaxy. So the looseness of their gravity, the way they're triggered into forming, their youth, and their position does indeed say they're distinct population inhabiting the disk. Globular clusters are larger, more massive, contain hundreds of thousands up to a few million stars. They're spherical in their distribution. Their internal gravity keeps them spherical, and they occupy elliptical orbits in the halo. Now, some of them, of course, just because of where they are in their orbit, could be seen near the disks. There are globular clusters that are found that seem at the moment to be in a disk, but that's probably just because they're passing through on a highly elliptical orbit. But generally, they have very low metal abundance. They're very old. They're very red stars, large numbers of them, and they are found in the halo. So two distinct populations.
Astro 1511 asks, is it possible to have a degree in engineering and astronomy at the same time, either as a double degree or like a major and minor degree program?
It's an interesting question, and I get asked it occasionally. It's challenging, and it's just challenging, unfortunately, because of the way universities are structured. And it's because astronomy is typically in a college of science and engineering is its own school or college. And making double degrees in many universities, some make it easier than others, is a challenge. And that's because engineering degrees is a sort of pre-professional qualification, and they have accreditation requirements. So it's a very strict sequence of courses you have to take when you're doing an engineering degree, and you don't have a lot of latitude or electives because you have to follow a pretty strict progression. In a science college, you tend to have a little more latitude. You can be a major in astronomy and you could have a major in astronomy and a minor in art or some other humanities field. That's possible. So it's sort of, unfortunately, the engineering side of the equation that makes the double major there hard. I'd say not impossible. I've met a couple of kids who've done it, but it's very challenging.
The next question is, when planning space missions, do astronomers have to constantly revise their calculations since the Hubble expansion changes with time?
It's an interesting question, and the basic answer is no, because the Hubble expansion and its derivative, the change of the expansion rate, which we think is now accelerating based on dark energy measurements, first done 15 years ago, it's a very subtle effect. So one of the most challenging observations in cosmology that people have been trying to do for a while without success so far is to actually measure directly measure the changing expansion rate of the universe, sometimes using distant probes like quasars at doing high resolution, high accuracy spectroscopic measurements. And those are very challenging and have not succeeded. It's viewed that a minimum of a decade of data will be needed to make that measurement. So the basic answer is no. Space missions are occupying short enough time frames that the change in the expansion rate of the universe is just tiny.
Slight Quills asks, how will the red giant phase of our sun change the rocky planets? Will they simply vaporize?
It's not clear that they will completely vaporize. What will vaporize, however, are the oceans and probably the atmospheres of the rocky planets, if they have them. I mean, Mercury obviously doesn't have an atmosphere, and Mars has a very thin atmosphere. But the red giant envelope, as it expands outwards, is very hot and has a lot of kinetic energy too in that phase. So it will certainly destroy the biosphere, the hydrosphere, and the atmosphere of the planets, but it doesn't have sufficient energy to fully ablate or blast away the planet itself.
The next question is from K-Pad Waith, who asks, what are the factors that affect the height and shapes of extraterrestrial life? And does it depend on gravity?
We imagine that it will. So we haven't detected extraterrestrial life, but it doesn't stop people speculating, and they have to use the Earth as an example. So, the shape of terrestrial life forms when they're not microbes are quasi-spherical, is a function of gravity. And I guess the biggest way we can talk about how that works is by looking at what difference between animals and plants that are on the land and creatures that are in the oceans. So in the buoyancy of the oceans, you can obviously have a much wider range of shapes and architectures of sea creatures than you do of terrestrial creatures, because they're not driven or bounded by gravity, because they live in a buoyant situation. They're essentially bounded by the pressure at the depth they operate in the oceans. And so you have, essentially spherical creatures with unusual shapes, and then you have fish, of course, that are designed to move rapidly through that environment. On the land, gravity is dominant, and so you have architectures of species that mean they have to sustain their strength. And some people have even done simplistic calculations to show there's a maximum size of an animal in the gravity of the Earth before its bones will just break from its own weight, because as you grow a three-dimensional object, its volume and mass grow quicker than the cross-sectional area of the bones. And so at some point, the bones are unable to keep up with the growing mass. And that has led people to posit a natural maximum size of animals on the land.
Zarukal, who's on with us live, asks, if you could give one gift of friendship to alien visitors from outer space, what would it be and why?
I don't know. That's a good question. I would say the one gift I would make would be, don't make the mistakes we made. So, if you learn from your mistakes, then you possibly can help another species from other parts of the universe that has not faced those mistakes, and maybe doesn't have the same technology to hurt their environment. So we've obviously taken great liberties with our global environment and our climate, and we know what we did wrong and we know how to fix it. So the lesson we could give to aliens is, we understand these things, we've fallen into these traps, and here's what you do not to fall into these traps, so maybe you can avoid them.
The next question is from Luis with a whole bunch of numbers. As cosmic radiation is one of the major obstacles for space travel, what do you think are the best solutions to explore to protect future astronauts from these harmful particle rays? This
is a tough problem, space radiation for long voyage travel through the solar system or beyond. There are no simple answers, but there are technologies that we haven't yet deployed. The simplest answer, which is not very helpful, is you just have a battle-hardened spacecraft with, heavy elements, metals, cladding that's, feet or meters thick to protect from this radiation. That's implausible if we have to launch such objects from the Earth, because the cost of launching metal and large amounts of material is prohibitive. However, if we get to the point of building infrastructure in Earth orbit, then assembling and for instance, mine asteroids or mine the moon to get those materials and assemble in Earth orbit and don't have to lift the whole thing from the Earth's surface, or we have a lunar elevator, for example, then we can make a heavy enough spaceship to be protected against radiation. So that would be one technology. The other way to do it is slightly more indirect. I mean, the other way to do it is essentially to put like a force shield around a spacecraft where you set up an electromagnetic induced field that will deflect the particles, the charged particles that are coming in. So that will work for the charged particles, which are the cosmic rays, and they're very high energy, very damaging, but it actually won't help the radiation. So you have a different problem for the charged particles, cosmic rays, and for the radiation. And there's no simple answer to the radiation, unfortunately.
We have time for just a couple more questions. It's 10:59. Robert Brady sent an email asking, black stars, such as the sun will eventually be, may have resident heat. Will the Webb telescope be able to find a lot of these dead stellar cores?
The Webb telescope will do a good job. It has limited field of view. So the James Webb is extremely sensitive, a large telescope. It's in a cold place and has great infrared instruments, but it can't do surveys very well. It's limited in the field it can cover. And so when it's looking for rare objects, very interesting rare objects like dark stars or brown dwarfs or whatever, it's kind of limited in its depth of its surveys. But yes, the James Webb definitely has the ability to detect the darkest objects in space, the coolest, the white dwarfs that have been cooling the longest, the brown dwarfs. There are no fully black stars, of course. Every star corpse, except for a neutron star or black hole, does have some radiation to detect, but James Webb will be able to take them individually, but it won't really have the scope of field of view to survey for them very efficiently.
Excellent. The next question is from Astro 1511. How exactly do ice volcanoes, or could ice volcanoes predict the presence of life, perhaps on Pluto to be specific?
Well, so the issue here is it's called cryovolcanism for planetary geologists. And it's the idea that in the outer parts of a solar system, very far from the sun, you can have a geological activity that will propagate up through cold material and add energy and essentially create volcanoes that emit literally spew out ice or water at some level along with magma as a normal volcano would. The fact that cryovolcanism we think exists, and we think we know some places where it exists, doesn't necessarily implicate life. However, except in a general sense that life needs a chemically dynamic environment. So in the early Earth, for example, it was sort of undersea volcanoes that probably added a lot of the chemical free energy that life depended on early in the oceans. And cryovolcanism might do something analogous in a cold world in the outer solar system. So in a very general sense of sort of available chemical energy, potentially fueling biology, ice volcanoes are interesting and important, and a place that has ice volcanoes could indeed have life. That's probably good enough for today because we're at our time, and thanks for your questions. And as good as always, very varied today, and for Vicky for helping and Matthew for facilitating, and we'll be back with you. I don't remember when, but I think we have another one on the books.
2 weeks,
on
okay. April 27th.
Yes, so actually 2 weeks right today and the same time and same day, actually 2 weeks.
Yep, and that will be on YouTube, and we'll send out the announcements. So if you go check out our YouTube channel, which is called Astronomy State of the Art, and you can like and subscribe and click the bell icon there. And then in next month, we will be back here on Twitch. So thank you all for joining us.
Okay, bye everyone.